In today's lesson, we're going to talk about similar solids. When we talk about similar, we are looking at the same shape, but not the same size. So we could have two cones, but one is larger than the other, one is smaller. Two solids are similar if the ratio A:B of their corresponding linear measurements are equal. So we're talking about linear measurements such as length, width, height, slant height, radius, diameter, and circumference, along with perimeter. When we talk about corresponding, this word corresponding really is just saying that we're talking about matching. We want to find the matching one. So if I'm looking at the height of one, I need to look at the height of my other solid as well. For our directions here for these three problems, we determine whether the solids below are similar. If yes, give the scale factor in simplest form. Let's go ahead and do these problems. So, my first problem, I have two solids, two cones, one's clearly larger, one's clearly smaller. I don't know if they're similar yet. I have to see if they have the same scale factor. What we're going to do is we're going to match our measurements. So here is my radius. 14 is my radius for the larger cone. My radius for the smaller cone is 4. So I'm going to do a fraction of 14 over 4. I got to simplify that. You always want to simplify. It says in our directions too in simplest form. So I'm going to go ahead and simplify that. If you're not good with fractions, Desmos helps you out a lot, so I'll go there just to show you how to do it. We type in that ratio. 14 over 4, 3.5 is a decimal, but over here with our little fraction symbol, we can get the simplified version, which is 7 over 2. So that simplifies to 7 over 2. Now let's look at my heights. The height of the larger cone is 20, and the height of the smaller cone is 6. 20 over 6. Again, I can go to Desmos to simplify that. Typing it on in, 20 over 6 comes out to be 10 over 3. Those are not the same fractions. They have to be exact same simplified fraction in order for them to be similar. So in this case, we would simply put no. No scale factor is needed because they are not the same. Let's look at our prisms for number 2. Again, same thing, set up your matching linear measurements. So this I'm going to call my length. This 10 over here, I'm going to call my width. Same thing with the 6 over here. And then we have the height of each. As we can see, the one on the left looks smaller than the one on the right. We want to see if they're similar. Let's check out their fractions. 6 over 10. Remember, you could write that as 6:10. Both are seen as a ratio and both are accepted as a ratio. But when I'm simplifying, I think it's easier to do this. So 6 over 10, again, I can go to Desmos, 6 over 10 turns out to be 3/5, 3 over 5. I'm not going to do my width because it's just 6 over 10 again. So I don't even need to go to Desmos for that one. My width is going to be 3 over 5. It's the same exact numbers. But then I got to check my height. My height is 8 over 12. Let's go to Desmos, see what 8 over 12 simplifies to. 8 over 12. Hit the fraction bar again. That's 2/3. So I do not have the same fraction for the last one. Even though the first two, the length and the width, were the same ratio, I cannot say they're similar because that last ratio was not equal to 3/5. So you always have to check all the dimensions they give you. My answer again here is no. Let's look at a last problem, number 3. Again, match up your linear measurements. Looks like I got a height for both. Even though the second one's laying on its side, that's okay. That's not the height. We cannot put that. We got to make sure the height is going to be 25. So just make sure you're really careful with where they are oriented, these shapes. The first two, they were kind of lined up really nicely. This last one, the cylinder is on its side. Then for my radius, I have a radius of 10 over here, but take a look. 24 is talking about the whole length of the diameter. I just need half of that as my radius. So 24 divided by 2 is going to give me 12 as my radius. So if you put 24 over 10 in your fraction, that would be incorrect. I have to use 12 and 10 like linear measurements with like linear measurements. 12 over 10 simplifies to 6 over 5. I could easily divide 2 from each of those to get 6. 10 divided by 2 gets me 5. Let's check our height. We have 30 over 25. One thing I want to mention too is that if I start, like in my numerator, I had this cylinder going first. I have to keep that consistent across all of the ratios. So I can't put 25 over 30. I couldn't go from my second to my first. I want to keep consistent with which shape I am choosing in my numerator to keep that consistent to see if the ratios are the same. 30 over 25 actually does simplify to 6 over 5. You divide 30 by 5 to get 6, 25 by 5 to get 5. My answer here is yes. Now how I state my scale factor is just by saying 6 to 5. You can write it as that, or you can also write it as the fraction it was, 6 over 5. Both are appropriate ways to represent a ratio. Next, we're going to look at comparing volume and surface area. So when we have these similar solids with this certain scale factor of A to B, remember that's A colon B, but we pronounce it and describe it as A to B, then their volume and surface area ratios are as follows. For surface area, we're going to have A squared to B squared. So we're going to be squaring both the A number and the B number. For volume, it's A cubed to B cubed. So we're going to be cubing that number for A in the scale factor and cubing that number for B in the scale factor. How I remember is I think about solving for surface area, we always had our units squared. When solving for volume, we always had our units cubed. So that helps me remember that I need to square the values for surface area and cube the values for volume. Let's get started. So here we're going to identify the scale factor or ratio. So we're solving for scale factor or those ratios for each pair of similar solids. Note we're given that the solids are similar, so we don't have to determine if they are similar or not. It's given that they are. One thing I want to remind us is that we always want to simplify first. In this case, we're given the scale factor we'll want to simplify first, but you always want to simplify your fraction first. So let's get started. Number 4, we have all these linear measurements to our triangular prism. So what I'm going to do is just choose one, because again, like I said, I know they're similar, so I know the fractions will be the same. So let's look at their heights, 6 to 3. Simplify that, super easy, turns out to 2 over 1. So my scale factor, what I just solved for, remember scale factor is that linear measurement. In that case, the height is a linear measurement, so I have 2 to 1 as my AB. For surface area ratio, I'm going to take A and square it, and then take B and square it. So super easy, I get 4 to 1. That is going to be my surface area ratio. Last but not least, for volume ratio, I gotta cube my A and B. Be super careful, don't cube the number 4. That's the surface area ratio. I have to go back to that scale factor ratio, cubing the 2 and the 1. So 2 cubed is 8, and 1 cubed is 1. That's going to be my volume ratio for these similar solids. For number 5, we have 2 similar cones. Again, want to look at one of those linear measurements. I'll look at the radius here and the radius for my larger cone to the right. So my ratio is 4 to 6. I'm going to simplify that. Again, if you're ever confused, go to Desmos. I'll type in 4/6. Hit the little simplified fraction button to get 2/3. So that is my scale factor. Again, scale factor is just the ratio of those linear measurements. I was talking about the radius there, which is a linear measurement. My scale factor, A to B, is 2 to 3. For surface area, we're going to take those numbers and square them. 2 squared and 3 squared. 2 squared is 4. 3 squared is 9. Last but not least, for our volume ratio, I gotta again go back to scale factor and do 2 cubed and 3 cubed. That's going to give me my answer. If you're uncertain what those get you, you can always go to Desmos, type in 2 cubed, gives me 8, and 3 cubed gives me 27. So I have 8 to 27 as my ratio for the volume. Our note here states that when given surface area or volume, we must always refer back to the scale factor first. In order to work backwards, we're going to use the square root when we have to go from surface area ratio to the scale factor. And I'll also use the cube root when I'm going from the volume ratio backwards to the scale factor. Let's take a look here. Our directions state again that we're identifying the scale factor or ratios for each pair of similar solids. So as you see in problem number 6, we are given the volumes of each shape. So I can make that into a ratio 162 over 384. So again, we're given the volume ratio, not the scale factor. We're not given any linear measurements here. The length, width, or height we do not know in this rectangular prism. So right away I go ahead and type this on Desmos. I type in 162 over 384. I click my simplified fraction button to get 27 over 64. So that's going to be my volume ratio because that's what I was looking at. I was looking at their volumes. So we're going to have 27 to 64. To work backwards, we have to go to the scale factor first. I can't go straight to the surface area because surface area is a squared to b squared. I don't know what a and b are yet, so I'm going to solve for it by working backwards. To work backwards, I do the cube root because volume is a cubed to b cubed. I have to do the opposite operation, which would be cubing these numbers. So I do the cube root of 27 and the cube root of 64. We can go ahead and do that in Desmos. Remember, you can hit the keyboard down here, go to Functions, we go to Miscellaneous, and we look at this one with n. Because again, I can put in, once I delete this, I can put in a 3 in that blank space outside the radical to make it a cube root of 27, which would be 3, and 64, which would be 4. So when working backwards, I get 3 to 4 as my A to B. Now, since I know A to B, I can go straight to surface area by squaring these numbers. 3 squared to 4 squared, well, that's going to be 9 to 16. For problem number 7, we're given the two surface areas. The surface area of the larger cylinder is 735, and the surface area of the smaller cylinder is 375. So again, don't forget, let's make a note here that we always want to simplify our ratio first. Just like we simplified scale factor when we had it first, we want to simplify our volume or surface area ratios first. So I go to Desmos, I type in 735 over 375, hit my simplified fraction button to get 49 over 25. That is going to be my surface area ratio. So right away I put that in for surface area ratio. 49 to 25. Okay, now I can't go straight from surface area to volume because I need to find my scale factor, what that A value is and what that B value is. So I'm going to work backwards. I'm going to take the square root because remember surface area is squared. So I have to undo that by doing the square root. The square root of 49 is 7, and the square root of 25 is 5. That's my A to B. Now I can go to volume ratio by cubing these numbers. 7 cubed to 5 cubed. Well, 7 cubed is 343, and 5 cubed is 125. That's going to be my volume ratio. Let's take a look here in problems number 8 and 9 where we're not given a visual but still asked to do the same thing. So we're asked in the directions to identify the scale factor or ratio for each pair of similar solids. Okay, problem 8. Solid A is similar to solid B. The ratio of the height of solid A to the height of solid B is 7 to 3. Find the ratio of the volume of solid A to solid B. So right away I simplify that ratio. Well, 7 over 3 is already simplified, so I am all good there. Let's use a pen to figure out how we get to our volume ratio. So I have A to B. That's my 7 to 3. To get to my volume ratio, I'm working forwards, not backwards in this problem. That's okay, because I can cube these numbers to get to my volume ratio. Remember, volume is cubed units, so I'm cubing those two numbers, my scale factor. And I know it's the scale factor because it's a linear measurement of height. 7 cubed is that 343. 3 cubed is my 27. That's going to be my volume ratio answer. For problem number 9, we have cone A is similar to cone B. The ratio of the volume of cone A to cone B is 64 to 1. Find the ratio of the surface area of cone A to cone B. So I'm going to go from the volume ratio to the surface area ratio. Let's take a look here. 64 to 1. That's already simplified, so I'm all good. So I type in or write 64 to 1. That is my volume ratio. So that's going to be A cubed to B cubed. That's my volume ratio. Okay, I can't go straight to surface area because I need to find out what A to B is in order to square it for surface area. So to work backwards, I undo that cubed. To get plane A and B, I got to take the cube root of 64 and the cube root of 1. So that's going to give me just plane A to B, my scale factor, which is going to be 4 to 1. Now, I'm not done here, can't stop here because I need to find the ratio of the surface area. That's what I'm looking for in this case. So, I keep going. And to get to surface area, I just square these numbers. So I do 4 squared to 1 squared. 4 squared is going to be 16. 1 squared is going to be 1. So my answer for the surface area ratio between cone A to cone B is 16 to 1. Always make sure that in your ratios, your scale factors, you want to make sure that you are stating and representing it like it's saying it needs to be. So for example, if I need the ratio of cone A to cone B, cone A needs to be the first number listed. So that's talking about cone A, and cone B needs to be part and related to the second number listed. Next, we're going to note that when you need to find a linear measure, surface area, or volume of one of your similar solids, this is not going to be when you're solving for the scale factor, surface area ratio, or volume ratio. You can set up a proportion to solve in this case. So that will be for 10 and 11, we'll set up a proportion, and here's why. For number 10, the ratio of diameters of two similar cylinders is 3 to 5. If the surface area of the smaller cylinder is 378 inches squared, we want to find the surface area of the larger cylinder. So right away what I'm finding is the surface area of the larger cylinder. Not the ratio like we've been doing, but just the plain flat out surface area of the larger cylinder. So we're going to set up a proportion here. Here's how. First I'm going to take the 3 to 5 they gave me. That's already simplified. Great. 3 to 5 is talking about my scale factor because it's based off linear measurements of diameter. Remember, diameter is a linear measurement, so that is going to be my regular scale factor, a to b. I need to solve in this case for the surface area. So I need to look and relate to my surface area ratio. That's going to be when I square A, so 3 squared, and when I square B, so 5 squared. That's going to be 9 to 25. I set that up in my proportion. Remember, proportions are two ratios equal to each other. That's my first one. Second one, I'm going to use the 378, but I got to be super careful what I put it. In my numerator, I'm going to put all the information for my small cylinder. In the denominator, I'm going to put all the information for my large cylinder. Why is that the case? Because 9 is my smaller number, 25 is the larger number. That's how I know it's small over large. When I go ahead and put this 378 in, I need to put it in my numerator. It's talking about my smaller cylinder surface area, so it has to go in the numerator. Denominator has to be x because that's what we're solving for, the larger cylinder surface area. Once I set up my proportion based off the surface areas, I cross multiply. 9 times x is equal to 25 times 378, which is 9,450. When I divide by 9, my answer comes out to be x equals 1,050, and my units here are talking about inches squared. That is going to be my answer for the surface area of the larger cylinder. For question number 11, we're going to set up a proportion as well because here's our problem. We have cone A and cone B are similar. The surface area of cone A is 108 millimeters squared, and the surface area of cone B is 147 millimeters squared. If the volume of cone B is 857.5 millimeters cubed, find the volume of cone A. So right away, what am I looking for? I'm looking for the volume of cone A. That's what I need to find. I'm not looking for the volume ratio. I'm looking for the specific volume of cone A. Let's go ahead and set up our ratio. So I was given 108 to 147. I'm going to go ahead and simplify that in Desmos to help me out because you always want to simplify your ratio first. So that was 108 over 147. I hit this little fraction button over here. That gets me 36 over 49. So that is the simplified version of this surface area ratio. So again, that's going to be my surface area ratio. So that's talking about a squared to b squared. 36 to 49. So I need to get the volume ratio. But remember, we have to go back to scale factor first. So my first step is I need that A to B. I can't go straight to volume. I kind of have to go around the corner. So when I'm working backwards, when I'm going from surface area to scale factor, I take this square root. I got to get from A squared to just plain A, and same thing from B squared to just plain B. So the square root of 36 is 6. And the square root of 49 is 7. Now, from my scale factor, I can go to my volume ratio. My volume ratio will be A cubed and B cubed. Again, I go ahead and do 6 cubed, which comes out to be 216. And I do 343, which is what 7 cubed is. Now I'm going to use this in my volume ratio. So 216 over 343 equals my volume amount. So I have to figure out where I'm putting this 857.5. That's going to go in my denominator because that's talking about cone B. So I can label this as putting all my information about cone A in the numerator and all the information about cone B in my denominator. X is going to go on top. Why? Because I don't know the volume of cone A, so I have to leave that as an unknown variable x. I cross multiply. 216 times 857.5 is 185,220. That's going to equal my 343x. I divide each side by 343 because I want to get x by itself. My answer comes out to be x equals 540. That is going to be the volume of cone A, so we're talking about millimeters cubed in this case. Alrighty, so that is our lesson for today. Thank you very much for listening.